Welcome to this walkthrough of LeetCode problem number 67, add binary. In this problem, we'll explore how to compute the sum of two binary strings and return the result as another binary string. Let's dive into the problem, analyze the approaches, and break it down step by step. In this problem, you are tasked with adding two binary strings and returning their sum as another binary string. The inputs are two strings, A and B, which represent binary numbers. For the output, you need to calculate their binary sum and return it as a string. Let's look at an example. If A is 11 and B is 1, the output would be 100. This is because, in binary arithmetic, adding 11, which is 3 in decimal, and 1, which is 1 in decimal, results in 100, which represents 4 in decimal. The result is always returned as a binary string, matching the format of the inputs. To build on this, let's consider another example. If A is 1010 and B is 1011, the output will be 10,101. Here's why: 1010 in binary is equivalent to 10 in decimal, and 1011 in binary is 11 in decimal. When you add these two numbers together in decimal, you get 21, which is represented as 10,101 in binary. Similarly, if both input strings are 0, the binary addition is straightforward and results in 0. The function needs to handle all such cases and return the correct binary sum as a string. Now, let's review the constraints and some edge cases that the solution must account for. First, the length of each input string can range from 1 to 10,000 characters, meaning the function must handle very large binary numbers efficiently. Additionally, both input strings will only contain the characters 0 or 1, and neither will have leading zeros, except for the special case where the string itself is 0. For edge cases, you should consider scenarios like when one string is much longer than the other, such as 1 and 1000000000000000000. Another scenario is when both strings consist of the same digit repeated, for instance, 11,111 and 11,111. You also need to handle cases where the result requires an additional bit, like adding 111 and 1, which results in 1000. Lastly, if one of the strings is 0, the output should directly match the other string. These considerations ensure the implementation is robust and handles real-world inputs seamlessly. To solve the add binary problem, we need to compute the sum of two binary strings and return the result, also as a binary string. This involves binary arithmetic, which operates in base 2. Let's consider a few different approaches to tackle this problem. First, we have the brute force approach. Here, we convert the binary strings into integers using Python's int function with base 2, add the integers together, and then convert the sum back to binary using the bin function, stripping off the prefix. While this method is straightforward and leverages Python's built-in tools, it has some drawbacks. It relies heavily on library functions, which means it doesn't showcase an understanding of binary arithmetic fundamentals. Furthermore, it's not portable to languages that don't have built-in utilities for binary conversions. While the time complexity is efficient at O, max, len, A, len, B, this approach is not typically ideal for interviews where demonstrating algorithmic knowledge is critical. A more refined solution is the digit-by-digit simulation approach, which directly mimics the manual process of binary addition. Here, we process the binary strings from the rightmost bit to the leftmost bit, just like how we perform addition in base 10. We maintain two pointers, starting at the last indices of the strings, and a carry variable initialized to 0. As we iterate, we extract the current bits from both strings, or treat them as 0 if the pointer is out of bounds. We then calculate the sum of the two bits along with the carry. The resulting bit is appended to the output string, and the carry is updated for the next iteration. Once all bits and the carry have been processed, we reverse the string to produce the final result. This approach is intuitive, avoids reliance on built-in functions, and is efficient with a time complexity of O, max, len, A, len, B. It's also space efficient, requiring only enough memory to store the output string. This makes it a strong choice for solving the problem, particularly in scenarios like interviews, where clarity and understanding of binary operations are key. Another possible method is the recursive approach, where we use recursion to simulate the addition process. At each step, we add the least significant bits of the two binary strings along with the carry, and recursively process the remaining bits until both strings are exhausted. While this approach is elegant and conceptually reduces the problem size at each step, it is less practical for several reasons. First, recursion introduces overhead due to the call stack, which can lead to excessive memory usage. For very large inputs, this could even result in stack overflow. Although its time complexity is still O, max, len, A, len, B, the space complexity becomes O, max, len, A, len, B, as well, due to the recursive depth. For these reasons, the recursive approach, while interesting, is not the most efficient or reliable solution for this problem. Instead, we choose the digit-by-digit simulation approach as it is both iterative and avoids the limitations of recursion, making it more robust and scalable for larger inputs. When solving this problem, it's essential to understand a few key observations about binary addition. The basic rules are simple: 0 plus 0 equals 0, 1 plus 0 equals 1, 0 plus 1 equals 1, and 1 plus 1 equals 0 with a carry of 1. This carry propagates to the next column, just like in decimal addition. By processing the binary strings from right to left and maintaining a carry throughout, we can directly compute the result without needing to convert the strings to decimal. Comparing the three approaches, brute force, recursion, and digit-by-digit simulation, each has its pros and cons. The brute force method is quick to implement but doesn't demonstrate algorithmic understanding and lacks portability. The recursive approach is elegant but suffers from practical issues like stack overflow for large inputs. The digit-by-digit simulation, on the other hand, strikes the perfect balance between efficiency, clarity, and simplicity. It avoids reliance on built-in functions, works well for large inputs, and demonstrates a strong understanding of binary arithmetic. For these reasons, it is the optimal choice for solving this problem effectively. To tackle the problem of adding two binary strings, we use a digit-by-digit simulation approach, similar to performing manual addition with decimal numbers. The process starts by reversing both input strings, A and B. This reversal allows us to begin the addition from the least significant bit, or the rightmost digit, and work our way leftward, which is more intuitive for iteration. For example, if the input strings are A equals 101 and B equals 11, reversing them results in A equals 101 and B equals 110. Once the strings are reversed, we initialize essential components for the calculation. We set up two pointers, I and j, to traverse the reversed strings, starting at position 0 for both. Additionally, a variable called carry is initialized to 0 to manage any carryover from the addition. Finally, we prepare an empty list called result to store the sum of each column as we process the digits step by step. The next step involves iterating through the digits of both strings until all digits have been processed and there is no carry left. This is done using a loop that continues as long as either pointer, I or j, is still within the bounds of their respective strings, or the carry is non-zero. During each iteration, the current digit of A is retrieved if the pointer I is within bounds, otherwise, it defaults to 0. Similarly, the current digit of B is retrieved or defaults to 0 if J is out of bounds. For instance, given A equals 101 and B equals 11, when I equals 0 and J equals 0, the digits are A, I equals 1 and B, J equals 1. These digits are then added together along with the carry. The sum, or digit underscore sum, determines the new binary digit to add to the result, which is calculated using digit underscore sum %2. The carry for the next iteration is updated using digit underscore sum //2. This new binary digit is appended to the result list, and both pointers, I and j, are increment to move to the next digits. Once the iteration is complete, there may still be a remaining carry. If so, this leftover carry is appended to the result list to ensure no value is lost. Since the binary digits were computed in reverse order during the process, the result list must be reversed to obtain the correct final order. After reversing, the list is converted into a string by joining its elements. For example, if the intermediate result is 0, 0, 1, 1, reversing it gives 1100, which is the correct final binary sum. The resulting binary string is then returned as the output of the algorithm, completing the process. There are several key insights about this algorithm that are worth highlighting. First, the rules of binary addition are straightforward: 0 plus 0 results in 0, 1 plus 0 results in 1, and 1 plus 1 results in 10, where the result is 0 and the carry is 1. These rules allow us to compute each column's sum easily. Second, reversing the string simplifies the implementation by ensuring we start with the least significant bits, eliminating the need to calculate indices from the end of the strings. Additionally, the algorithm handles edge cases seamlessly. For instance, when the input strings are of unequal lengths, it treats missing digits as 0. It also ensures that carry values are propagated fully until no carry remains. Even empty strings are handled gracefully by treating them as having a value of 0. To implement this algorithm efficiently, we use a few simple data structures. The result list is used to store intermediate binary digits during the computation because appending to a list is more efficient than concatenating strings repeatedly. The pointers I and j are crucial for traversing the two strings simultaneously, ensuring that digits of different lengths are handled correctly. The carry variable plays a vital role in managing overflow from one column to the next, enabling accurate binary addition across all digits. Together, these data structures ensure that the algorithm is both efficient and robust in handling a wide range of input cases. This implementation adds two binary strings by simulating binary addition from the least significant bit, rightmost digit, to the most significant bit. We start by initializing an empty list to store the result and a carry variable to handle overflow during addition. The indices I and j are initialized to point to the last characters of strings a and b. We loop while there are digits left to process in either string or there is a non-zero carry. For each iteration, we extract the current digits from a and b if their indices are valid, otherwise, we use 0 for out-of-bounds indices. Next, we compute the sum of the two digits and the carry. The new binary digit is the remainder of the division of this sum by 2, total %2, and the carry is updated to the quotient, total //2. The new digit is appended to the result list. Once all digits are processed and the loop ends, the result list will contain the binary sum in reverse order. We reverse the list and convert it to a string using join to get the final binary representation. This approach handles all edge cases, such as inputs of different lengths and the presence of a carry after processing all digits. The algorithm has a time complexity of O, max, len, A, len, B, since we process each digit once, making it efficient for large inputs. Here, we begin by defining a public class called solution and implement the method addBinary, which takes two binary strings, A and B, as input. To store the result, we use a string builder object named result. This is because string builder allows us to efficiently build the final output. Additionally, we initialize a variable called carry to 0. The carry will help us handle situations where the sum of digits exceeds 1 in binary addition. Next, we set up two pointers, I and j, to traverse the input strings from right to left, starting from the last indices of A and B, respectively. These indices are determined using the length of the strings. Then, we enter a while loop that continues running as long as there are digits left in either string or the carry is greater than 0. Inside the loop, we retrieve the current digits from both strings. If a pointer goes out of bounds, we treat the corresponding digit as 0. This ensures that the loop handles strings of unequal lengths gracefully. We then calculate the sum of the current digits along with the carry. Using this sum, we determine the new binary digit to append to the result by taking the remainder when dividing the sum by 2, and we update the carry by performing integer division of the sum by 2. Finally, we decrement the pointers to move to the next set of digits in the strings. After exiting the loop, we have the binary sum stored in reverse order in the string builder object result. To get the correct order, we simply reverse the string builder and convert it to a string using the reverse and to string methods. This reverse string is our final binary result, which we return from the method. With this implementation, we can efficiently add two binary strings, accounting for all edge cases like different lengths and carry propagation. To solve the problem of adding binary numbers, we start with the first example where A is 11 and B is 1. The goal is to add these two binary strings and return their sum as another binary string. To do this, we initialize four key variables: result as an empty list to store the binary digits of the answer, carry as 0 to handle cases where the sum exceeds 1, and I and j as the indices pointing to the last digits of A and B respectively. In the first iteration, we take the last digits of both strings, which are 1 from A and 1 from B. Adding these together along with the carry, which is currently 0, gives us a total of 2. Since binary addition only allows values of 0 or 1, we append total %2, which is 0, to the result. We then update the carry to total //2, resulting in a new carry of 1. At this point, the result contains 0. Next, we decrement the indices I and j to process the next significant digits. In the second iteration, I is now 0, and j is -1, meaning b has no remaining digits to process, so digit_b is treated as 0. The current digit from a is 1. Adding 1 from a, 0 from b, and the carry of 1 gives a total of 2. Again, we append total %2, which is 0, to result, making it 0, 0. The carry remains 1 because total //2 is 1. We then decrement both indices again, so I becomes -1 and j becomes -2. In the third iteration, both indices are out of bounds, meaning both digit_a and digit_b are treated as 0. Adding these two zeros with the carry of 1 results in a total of 1. We append 1 to the result, making it 0, 0, 1. This time, the carry is updated to 0 since total //2 is 0. With no more digits to process and the carry cleared, we reverse the result and join the digits to form the final binary sum, 100. Now let's look at another example, adding the binary numbers a as 1010 and b as 1011. As before, we initialize the result as an empty list and carry as 0. The indices I and j are set to 3, pointing to the last digits of each string. In the first iteration, the last digits are 0 from a and 1 from b. Adding these along with the carry of 0 gives a total of 1. We append the binary digit 1 to result, making it 1, and the carry remains 0. After this, we decrement both indices to move to the next digits, so I becomes 2 and j becomes 2. In the second iteration, the current digits are 1 from a and 1 from b. Adding these together with the carry of 0 results in a total of 2. We append total %2, which is 0, to result, making it 1, 0, and update the carry to 1 since total //2 is 1. Moving on to the third iteration, I is now 1 and j is also 1. The digits at these positions are both 0. Adding 0 from a, 0 from b, and the carry of 1 gives a total of 1. We append 1 to result, making it 1, 0, 1, and reset the carry to 0. Finally, in the fourth iteration, I and j are 0, and the digits are 1 from both a and b. Adding these with the carry of 0 results in a total of 2. We append 0 to result, making it 1, 0, 1, 0, and update the carry to 1. After processing all the digits, we check if there is any remaining carry. In this case, the carry is 1. We add this to the result, making it 1, 0, 1, 0, 1. The last step is to reverse the result and join the digits together to form the final binary sum, 10,101. This completes the addition of a as 1010 and b as 1011. For our third example, we consider adding two binary strings where both are 0. When adding a is 0 and b is 0, the initialization step sets result as an empty list, carry is 0, and I and j both is 0. In the first and only iteration, the digits are both 0. Adding these with the carry of 0 results in a total of 0. We append 0 to result, making it 0. Since there are no more digits to process and the carry is 0, the final step is to reverse the result and join the digits, resulting in the binary sum 0. This concludes the example and shows how the algorithm handles the simplest case of two 0 inputs. The time complexity of that add binary function is determined by the length of the input strings, specifically the longer of the two. This is because the main operation involves iterating through the binary strings from right to left while also accounting for any carry. The loop runs until all characters from both strings are processed, and in the worst-case scenario, this requires a number of iterations equal to the maximum length of the two strings, which we denote as max, n and m. Inside each iteration, the operations such as accessing characters, converting them to integers, performing addition, and appending the result are all constant-time operations, or O1. After completing the loop, we reverse the result to obtain the correct binary sum. Since reversing a list takes time proportional to its length, and the result can have up to max, n, m, plus 1 digits, this step also takes O, max, n, m time. When we combine the cost of iteration and the reversal, the overall time complexity is dominated by O, max, n, m, making it the final time complexity for the function. The space complexity of the add binary function primarily comes from the storage used for the result. The result list holds the binary digits of the sum, and in the worst case, its size is equal to the maximum length of the input strings plus 1, accounting for a potential carry. This requires O, max, n, m, space. Beyond the result, the function uses a few auxiliary variables such as carry, I, j, digit underscore a, and digit underscore b, which only take constant space, or O, 1. Since the dominant space usage arises from the result list, the overall space complexity of the function is O, max, n, m. The time and space complexity of the add binary function remain consistent across best, average, and worst case scenarios. In the best case, where there is no carry during addition, the number of operations still scales with the length of the longer string, leading to a time complexity of O, max, n, m. On average, the same holds true because the number of iterations is proportional to the longer string, and the space required for the result is determined by the length of the output, which is also O, max, n, m. Even in the worst case, where every digit produces a carry, the time and space complexity remain O, max, n, m, as the carry only adds one extra digit to the result. When compared to a naive approach that involves converting the binary strings to integers, performing addition, and converting the result back, our solution is far more efficient. The naive method introduces overhead from repeated conversions, each of which takes O, max, n, m, time, and risks issues like integer overflow. By directly processing the binary strings, our solution avoids these inefficiencies and achieves optimal performance. The big O complexity of the add binary function can be mathematically proven by analyzing the operations involved. The loop, which processes the binary strings, executes at most max, n, m, times, and each iteration performs only constant time operations such as character access, addition, and list appending. This gives an iteration cost of O, max, n, m. After the loop, we reverse the result list to produce the final binary sum, and since the result length is proportional to the input size, this step also takes O, max, n, m, time. For space complexity, the result list grows linearly with the input size, as it holds up to max, n, m, plus 1 digits, leading to O, max, n, m, space. Auxiliary variables contribute only constant space and do not affect this analysis. Combining these observations, we conclude that the overall time and space complexity of the function are both O, max, n, and m. When working with binary addition, there are several common mistakes to watch out for. One of the most frequent issues is ignoring the carry. Remember that in binary, when the sum of 2 bits exceeds 1, you need to carry over the extra bit to the next position. For example, adding 1 and 1 results in 10, not 0, 1. Another mistake involves the misalignment of binary strings. If the two strings have different lengths, you need to pad the shorter one with leading zeros to ensure proper alignment. Failing to do this can lead to incorrect results. Additionally, converting large binary strings into integers for arithmetic might seem convenient, but it can introduce overflow issues or performance bottlenecks, especially in languages like Python or Java. Instead, it's better to perform the addition directly on the binary strings. Finally, don't forget about the final carry. If there's a leftover carry after you've processed all the bits, it must be appended to the result. For instance, adding 111 and 1 should produce 1000, not just 000. These are some of the most common pitfalls to avoid when solving this problem. Another issue to be mindful of is inefficient string operations. For example, repeatedly concatenating strings, like appending characters to a result string during each step of the addition, can lead to a time complexity of O, n squared, due to the immutability of strings in many programming languages. A better approach is to use a list to build the result and then join the list into a string at the end. Now, from an interview perspective, this problem is often used to test your understanding of binary arithmetic. You might be asked to extend the solution to handle inputs in other bases, such as base 3, or to optimize it for better performance. Be ready to discuss edge cases like one of the strings being empty, both strings being 0, or inputs that are extremely large. Interviewers may also challenge you to implement the solution without relying on helper functions like int or bin, which tests your grasp of low-level binary operations. Lastly, make sure to emphasize the time complexity of your approach. For this problem, a well-thought-out solution processes each bit once, resulting in a complexity of O, max, n, m, where n and m are the lengths of the two binary strings. This problem also shares similarities with other coding challenges, so practicing related problems can deepen your understanding. For instance, LeetCode number 2, add two numbers, involves adding integers represented as linked lists. Another similar problem is LeetCode number 415, add strings, which deals with addition in decimal rather than binary. LeetCode number 989, add to array form of integer, and LeetCode number 371, sum of two integers, which uses bitwise operators, are also worth exploring. Beyond the standard approach, there are some alternative methods to consider. One is using bitwise operations to simulate binary addition. Operations like AND, XOR, and left shift allow you to perform the addition without converting the strings at all. This method is faster for large inputs but tends to be more complex to implement and debug. Another option is a recursive approach, where you handle the addition bit by bit while propagating the carry. Although this can lead to clean and elegant code for small inputs, it isn't scalable, as large inputs could cause a stack overflow due to excessive recursion depth. Finally, there is the option of using built-in functions to simplify the implementation. By converting the binary strings to integers, performing the addition, and then converting the result back to binary, you can solve the problem with minimal code. While this approach is straightforward and easy to implement, it has significant trade-offs. Specifically, it is not memory efficient, especially for very large inputs, and might not be the best choice in an interview setting where optimization and scalability are often valued. In practice, this method can be useful for quick prototyping but is unlikely to impress in scenarios that require a deeper understanding of binary arithmetic or low-level operations. Carefully consider the trade-offs of each approach and choose the one that best fits the constraints and goals of the problem you are solving. Great job following along. In this session, we covered how to solve the add binary problem step by step. We summarized the algorithm, its complexity, and key takeaways to enhance your understanding. Keep practicing, and don't forget to like, subscribe, and share for more coding tutorials. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!